Hi guys, welcome to our week 2 content. So this week we're going to study about reaction feasibility. Now what is that reaction feasibility? So you may not heard of this feasibilities. What about reaction spontaneity? So I'm sure you heard about spontaneous reactions, right? So what is the first impressions of spontaneous reaction? Some student actually told me that spontaneous reaction is a reactions that react at a higher rate of reactions. It's a fast reactions. So in fact, spontaneity or feasibility is to measure reactions whether or not it happens without energy input. Okay, so let's say for example, I have compound A plus compound B. If I mix them together without any heating, A and B will spontaneously react to form C as a product, and this reaction is considered as a spontaneous reaction. All right, but if I add C with D, when I mix them together in a beaker, I don't see any reactions until I heat it up. So that is a non-spontaneous reaction because we need to heat it up before the reaction takes place. So basically, spontaneity or feasibilities are the same. They are referring to the same thing. It's about reactions, whether or not it reacts and it forms a product under inputs of energy or without any inputs of energy. So this is about reaction feasibilities. And it is important to know about a reaction feasibility before we carry out a reactions or before we carry out an experiment, because if we know that this particular reaction is not going to happen under certain condition, no point we actually conduct the experiments under these conditions, right? So this is a preliminary step before we actually conduct a real experiment. So we know that, okay, this experiment will never work at 25 degrees C. So we don't have to waste time to test these reactions under 25 degrees C. So we need to get all these clear before we conduct the experiments, and that will save us some time, some cost, not some, but it's actually a lot. And we can foresee the yield of the products under certain conditions. Okay, of course, the higher the feasibilities of the reactions, the more vigorous the reactions and the more products form, because you don't need to input energy and it will get the products for you. All right, so this is reaction feasibility. So maybe you're still not clear about this. Let me give you an actual example, a real life example. Let's say for example for rusting. What do you think about rusting? Is rusting a feasible reaction? Is rusting a spontaneous reaction? Now rusting is actually to convert iron into iron 3 oxide, right? So the important elements in these reactions will be iron, water, and oxygen. All right, if you have all three in these reactions, then it will rust. All right, so in this case, for rustings of ions, do we actually input energy? Do we actually heat it up? Do we actually add a catalyst for this reaction to take place? The answer is no. So rusting will happen by itself. But then, if you notice that rusting may take longer than expected. So some iron depends on the conditions, the humidity. So if some ions are exposed to water and oxygens more frequent, of course the rusting process is faster. But some ions are in a way under the protected environment. So this rusting process, it will still rust as long as water, oxygens, and iron is there. So it will still rust, but it takes longer time. So it does not matter whether a reaction takes a shorter time, higher rate, or longer time, slower rate. As long as it happened without an input of energy, we call that as a spontaneous or a feasible reactions. All right, let's look at the learning outcomes. Now, these are the learning outcomes we're going to cover. So number one is able to define and explain entropy, which we're going to cover it in a while. Able to define second and third law of thermodynamics. Yes, we need to know that because it's all about entropy here. Able to perform calculations for entropy change of reactions. Yes, definitely, because just like enthalpy change, when you get a positive enthalpy, you know it is an endothermic reactions. is absorbing heat for the reaction, and if you get a negative value, negative enthalpy, then you know it is an exothermic reaction. Same goes to entropy. We need to know whether an entropy is positive or negative, and what does it tell you about when you have different sign. All right, and able to determine reaction feasibility based on Gibbs free energy. Yes, that's the ultimate goal of this topic. Gibbs free energy calculations involve entropy. That's why we need to know about entropy first before we can apply in the Gibbs free energy equations. And that will tell us whether a reaction is spontaneous or not under certain conditions. All right, that's important. And Ellingham diagram, the last learning outcome will be a graphical presentations. These graphical presentations will give us the Gibbs free energy for most of the common reactions against a range of temperature. So from there we know under certain temperature range a reaction is actually spontaneous. But then if out of this range, whether it is lower or higher, a reaction becoming less feasible, less spontaneous, or non-spontaneous at all, no reaction at all. All right, so these will be the last things we learn. Now these are the important things for engineering aspect, because yeah, we are studying the process of a chemical reaction. We are not doing the chemical reactions when you're studying engineering. We are studying the existing chemical reactions and how to actually improve it in terms of its design, in terms of the raw material use, in terms of the energy changes, all right, in terms of the feasibility, how long it takes, whether we need to provide heat or not. So these are the things that an engineer should consider, okay, and they should be able to troubleshoot in an industrial process. All right, so let's look at law of thermodynamics, second law of thermodynamics, and third law. Now you may ask, what about first law? First law of thermodynamics is actually very simple. It's actually we can't actually create or destroy energy. Energy will always change from one form to another. We learned that, right? So this is the first law, that will be first law of thermodynamics. And second law of thermodynamics is actually on the total entropy of a reaction system and surrounding always increases for a feasible process. Now if you have a feasible reaction, just like rusting, okay, you are producing rust by mixing iron, water, and oxygen together, and God knows how long it takes, but yeah, as long as it starts rusting, all right, it starts to rust. So this is a feasible reaction, meaning that the total entropy of a reactions of this particular reaction, it's always increasing. It's always a positive value. Okay, so total entropy is referring to the entropy value of the system, which is the chemical reaction itself, the rusting process itself, as well as the entropy value of the surrounding. Okay, because when there is a heat change, when there is an entropy change in the system, that will actually affect the surrounding energy. Okay, so the total of system and surrounding together will give us an idea whether the entropy is a positive or negative, and that will tell us whether a reaction is feasible or not. You got that? So the third law of thermodynamics is actually at absolute zero, which is equivalent to 0 Kelvin or negative 273 degrees Celsius. A crystal lattice has a perfect order, hence zero entropy. Now from this third law of thermodynamics, maybe you can start imagine what is the meaning of entropy. When they say a crystal lattice has a perfect order, what does that mean by perfect order? They arrange in a ordered arrangement, a nice arrangement to form a cubic lattice structure. Let's say, for example, I have sodium chloride. You're forming a cubic lattice structure with perfect order. Sodium chloride, sodium chloride, sodium chloride. Okay? And this structure will have zero entropy at absolute zero. So what do you think about entropy then? So look at this structure. I mean this word. You can see the ink, all right, the ink that printed this entropy is actually changing, dispersing from the left to right. Look at that. These are all together in an ordered arrangement, right? They form a letter E, and then slowly it disperses out until the words blur. You see all the ink dots, they actually disperse out. So I can say here is an ordered arrangement, and here this referring to disorder. Okay, so ordered and disorder. So when entropy increases, when entropy is positive value, we call that the arrangement is in a disorder form. But when an entropy is 0 or entropy is a negative value, we call that as an ordered arrangement. Now, what arrangement we're referring to? The arrangement of the compounds involved in the reactions. Okay, so the definition is entropy is the measure of the amount of disorder in a system. We are measuring the degree of disorderness in the system. Let's say, for example, you are changing from solid into liquid. That's becoming disorder, right? The degree of disorderness is actually increasing, and you're changing from liquid into gas, even more disorder. So in this process, in these directions from solid into liquid, liquid into gas, we can see the entropy is increasing. All right, so the other way around, vice versa, if you're changing from a gas into a liquid, when you actually condense it, and from a liquid when you freeze it into a solid, then we can see the degree of disorderness is actually decreasing, hence resulting in a negative entropy value. Okay, so entropy basically is a value or an energy to measure the degree of disorderness, the arrangement of the particles in a system or in a reactions or even in a compound. All right, so let me give you an example. If I have Haber process, all right, 3 hydrogen gas plus nitrogen gas, you are changing into 2 ammonia gas. Now, based on these reactions, all the compounds involved are in gaseous, right? They're all in gaseous. Can I say the entropy is the same when we compare between products and reactants? Because they are all gases, they are all random motions. Not really. If you look at that, how many moles of gases on the left hand side, on the reactant side? Total, you have 4 moles of gas, right? And then how many moles of gas here on the left hand side as a product? You only have 2 moles of gas. So what does it tell you from here? 4 moles of gas and 2 moles of gas. Which side, the reactants or the product, is giving you a higher degree of disorderness? Obviously, the reactant side. So the reactant will have, this side will have low entropy value. Okay, on the product side we have high entropy. Oh, sorry, I messed it up. Here should have high entropy value. Here should have low entropy value, right? Because to measure the disorderness. So high and low, I have a high value here, I have a low value here. Let's say, for example, the high entropy change is about 100, and then for low entropy change, it is actually about 40, just an example. And what is the entropy change during this reactions when you change from the reactants into the products? So what is the entropy change? The difference between 100 and 40. So you just use 100 minus 40, and then you're actually getting 60. So 60 is the entropy change of this reaction, and this entropy change is actually the entropy change of the system. Still remember the second law of thermodynamics? We have to add up systems together with surrounding in order to get the total entropy, so that we can tell whether this reaction is feasible or spontaneous, right? So this is just to get the systems, and how do we do a full calculations to tell whether this reaction is spontaneous or not. So in the next video, I'm going to tell you how to do a calculations on this, to calculate the entropy systems, to calculate the entropy surrounding, in order to identify the total entropy, whether it is positive or negative. So positive, always remember, positive entropy means highly disordered. So when it's highly disordered, mean what happened is the energy in the system is disordered too, right? When the particles are spreading around, what happened is the energy is also spread around in a bigger surface, in a bigger volume. So when the energy are well dispersed, when the energies are well spread, then we can say the system is actually more stable. All right, so when I say total entropy is a positive value, means they are more disordered, so energy is also more spread out, hence the product form is actually more stable. Okay, so when total entropy is negative, meaning that the disorderedness is actually decreasing, they're getting more and more ordered, hence the energy is not spread out as well as the one in the disordered system. So the system is considered low stability or less stable. Hence, when total entropy is negative, meaning that the reaction is non-spontaneous or not feasible. All right. So I repeat, when total entropy is positive, it leads you to a more stable system, more stable product. Hence, the reaction is spontaneous. When the total entropy is negative, it leads you to a more ordered arrangement. Okay, so the system will become less stable, and hence the reactions is not feasible or non-spontaneous. All right, so this is in terms of energy, when we explain why positive and negative entropy will lead you to different types of spontaneous or non-spontaneous reactions. So that's it for this video. The next video I will explain in terms of the calculations. All right, thank you.